Hello, Professor Simon and the students who would like to hear my lesson. Today I will talk about navigating a banked turn, application of calculus of motion in space. In this video, I will teach how to analyze and model the motion of objects in three-dimensional space by using parametric equations and vector calculus. This includes deriving velocity and acceleration vectors, identifying centripetal and tangential complements of acceleration, and applying these concepts to real-world scenarios such as banked turns and projectile motion of my dog Audrey making a leap. Here, I will explain the motion vectors. Let Rt be a twice differentiable vector-valued function of the parameter t that represents the position of an object as a function of time. The velocity vector vt of the object is given by velocity equals vt equals to r prime t. And acceleration vector at equals to v prime t equals r double prime t. And speed, which also equals to the magnitude of velocity, also equals to the magnitude of velocity, or the magnitude of r prime t, or the derivative of position over time. Before we proceed to acceleration vectors, we need to remember the formulas of unit tangent vector and unit normal vector. Alright, now let's go through the acceleration vector derivation. Acceleration as a vector function is the derivative of the velocity vector. But we've already talked about the velocity vector being broken up into the speed, which is the magnitude of that vector, and then its direction, which is the unit version, and the unit vector of the velocity vector is the tangent vector unit. Tangent vector, so we're kind of holding off on the derivative and just saying, okay, velocity is made up of speed and direction. So now we can apply one of the properties of the derivative we saw. Basically the product rule for scalar times a vector. And like those product rules were the same, it was derivative the first times the second plus the first times derivative of the second. So go ahead and apply. And then we will want to recognize that the derivative of big T, the derivative of the tangent vector function is related to the normal vector. It just needs to be normalized. And so what we want to do is multiply on both sides by t prime of t. And then notice where we've gone, and so the derivative of the tangent vector function is going to be equal to that. And so it goes right here. And that's how you get from the first line to the second line. It's the exact same. Then we recognize that the curvature formula, one of the curvature formulas, relates to the magnitude of t prime and magnitude of r prime. And we do the same kind of thing where we multiply the magnitude of r prime on both sides. And it cancels. So we take magnitude of t prime and we replace it with curvature times magnitude of r prime. And we see the curvature there. This is the speed, right? And then the speed is one of those, it's just that one. R prime is the velocity and the magnitude of the velocity is the speed. So that is the speed. And then of course multiplying those two together we get v squared. So this writes the acceleration in terms of the two direction in tangential direction and the normal direction. And it says in the tangential direction, the acceleration is just due to change in the speed, which we already thought about. And here are some formulas that we need to remember before we proceed to the next question. Say hi, Audrey. Come on, say hi. Alright, here let's solve an example question, and we are gonna use the formulas from the last formula sheet. So for example, my dog Audrey has mass m. Well, that really sounds weird. Let's say that my dog Audrey weighs m pounds. Imagine that she moves in a circular pattern with constant angular speed, omega. Omega has position vector rt equals to a cosine omega t plus a sine omega t. Please find the force acting on her and show that she is directed toward the origin. So every time you see a cosine something and a sine something, then you will know that it runs in a circular pattern. So in Newton's second law, force at time t equals to ma, and rt vector equals to a cosine omega t and a sine omega t. So r prime t here equals to velocity, which also equals to negative a omega sine omega t and a omega cosine omega t. And let's keep going. So the derivative, so v prime t, velocity prime, equals to acceleration. And that equals to negative a omega squared cosine omega t and a negative a omega squared sine omega t. So force at time t here equals to ma, and that also equals to negative m omega squared times a cosine omega t and a sine omega t. And a cosine omega t and a sine omega t here equals to rt. So altogether, that force at time t equals to negative m omega squared rt. So that means force acts in direction opposite to the radius vector rt, which also means that it points toward the origin, because here it is negative. Here we will look at projectile and motion. Mass and omega squared has to be positive. Projectile motion, Newton's second law. Alright, here I will explain the proofs of the tangential acceleration and normal acceleration. Okay, so we have some assumptions here. First assumption is that we have constant mass. Only force acting on the object after launch is Earth's gravity. And we also assume the force of gravity is constant because the object is sufficiently close to the Earth. Alright, here we'll draw something. We have the ground here. So we have an object at a height, and the object is going to be thrown into a projectile motion. And that's what we are trying to solve here. Here we will rewrite f equals negative mg because our object is going down in the y direction. Well, although it's going up at first, it will go down eventually. Well, we know that f equals ma, so we will replace f into ma. And here we will cancel m. And what we get is a equals negative gravity j. And we are trying to find r of t right here. And here we will integrate it. And after we integrate, we will be left with velocity. So we are integrating negative gj with respect to t. So our velocity will become negative gtj plus c at time equals 0, and velocity equals v naught. So that leads to velocity at time equals to negative gtj plus v naught. So then if you want to find position, we need to integrate that. Well, I'm not gonna do the integration here, but that equals to negative half gt squared j, which equals to the physical formula of gravity equals half gt squared. But here we will also add v naught t and c2, and c is a constant. Well, we know that our initial position is s of 0, s naught. So that means c2 equals to s of 0, s naught j. So that means our position is negative 1/2 gt squared j plus v naught plus t plus s naught j. Well, we will rewrite this into another form, and here it is. And here we got a question, how do we express v of naught? Well, here I will draw something so we can better express the v naught formulas. Alright, here we will break v naught down into a horizontal position and a vertical one. So the horizontal position will become v naught cosine alpha, and the vertical will become v naught sine alpha. So altogether, v naught becomes v naught cosine alpha I plus v naught sine alpha j. So here we will replace v naught back into the formula. Altogether we will get RT equals to negative half GT squared plus S naught J plus T times V naught cosine alpha I plus V naught sine alpha J. Well, here we will express the position of x and y separately. So at time t, the x position will be v0 cosine of alpha time t. The position for y at time vt will be different. It will be at s0 plus v0 sine alpha times t minus half gt squared. Also, we can also solve the velocity in each direction. So the velocity at the x direction will just be v0 cosine alpha. And the velocity at y direction will be v0 sine alpha minus gt. And here we can tell that velocity from the x direction and velocity from the y direction is derived from xt and yt. So here I got a practice question for us to do. We will use the formulas derived from the last formula sheet. So the question is, Audrey made a leap with an initial speed of 80 feet per second at an angle of 30 degrees, and her initial height was 3 feet. So the first question is, what is her trajectory? Find it with parametric equations. So here we will write down x equals 80 cosine 30t first. And that becomes xt equals 40 square root 3. And our y will become 3 plus 80 sine 30t minus half 32t squared. And y of t will equals to 3 plus 40t minus 16t squared. Alright, here we got another question. The question is, how far did Audrey jump horizontally? And we know that since she lands onto the ground after she jumped, the height will be 0. So y equals 0. And y also equals to 3 plus 40t minus 16t squared. And after we use the parametric equations, we will find out that t equals to approximately 2.57 seconds. And x of time, 2.57, will equals to approximately 178 feet. And for the next question, what is the speed of her when she lands? And we already know that time equals to 2.57 seconds, and speed equals to the magnitude of velocity vector. And so we also know that velocity vector equals to r prime t, and that is equal to 40 square root 3 and 40 minus 32t. And altogether, we know that speed equals to a large bracket, 40 square root 3 bracket squared plus 40 minus 32 times 2.57 bracket squared. And that altogether equals to 81 feet per second. And that is Audrey's landing speed.